Find the soil classification. In this problem, we've been provided the grain size distribution plot and the Atterberg limits. The grain size distribution plot shows the results from a sieve analysis test, and the exact data from some of the points have been provided. The first step in classifying the soil is to determine whether the majority of soil sample by weight is fine grain material or coarse grain material. The percentage of fine and coarse grain material is determined from the plot based on the size of each soil type. Gravel is considered a coarse grain soil and refers to all particles larger than 4.75 millimeters in minimum diameter. Fines is the fine grain material, which consists of silt and clay, and refers to all soil smaller than 0.075 millimeters. Sand is a coarse grain soil and includes all particles smaller than gravel and larger than fines. The boundary points between these soil types are traced horizontally to the vertical axis, and we can compute the percentage of fine grain materials to be 10% of the entire sample by weight. The percentage of sand can be determined by subtracting 10% from 80% to get 70% sand. And lastly, the sample is composed of 20% gravel. Now that we have our percentages for the gravel, the sand, and the fines, we know we're dealing with a coarse grain soil. And since there is a larger percentage of sand than gravel, the soil is classified as a sand. Since there is no more than 12% fines by weight in the sample, we must calculate the coefficient of uniformity and the coefficient of curvature, which are based on the values of D10, D60, and D30. D10 refers to the diameter at which only 10% of the soil by weight can pass through. Here, our D10 value is 0.07 millimeters. Likewise, D30 refers to the diameter which only 30% of the soil by weight can pass through. The D30 value is 0.425 millimeters, and the D60 value is 0.85 millimeters. The values are plugged into the equations for D10, D30, and D60. The coefficient of uniformity computes to 11.3, and the coefficient of curvature to 2.8. Based on the ASTM standards, the sand is well graded if the coefficient of uniformity is at least 6, and the coefficient of curvature is at least 1 and at most 3. It turns out this sample is well graded. So far, we have a coarse grain soil, which is a sand, having 10% fine grain material, and is well graded. Lastly, we need to classify the fines as silt or clay. To do so, we look at the given Atterberg limits and plot the liquid limit on the horizontal axis by the plasticity index on the vertical axis. The abbreviations on the chart stand for low plasticity clay, low plasticity silt, high plasticity clay, and high plasticity silt. The liquid limit value of 50% divides the low and high plasticity soils. The A line separates the clay from the silt, whose equation is shown. The plasticity index is equal to the liquid limit minus the plastic limit, which in this case is 65 minus 40, or 25. The point is plotted and falls in the MH zone, which stands for high plasticity silt. Reviewing our possible solutions, The soil is a well-graded sand with silt. The answer is B.